Welcome to the video on quantities in chemical reactions, based on Chapter 8 of Introductory Chemistry by Nivaldo J. Tro. This video covers key topics including climate change and CO2, stoichiometric relationships, mole-to-mole and mass-to-mass conversions, theoretical and percent yield, and enthalpy in reactions. We begin with the impact of fossil fuels. The combustion of fuels like octane produces water and carbon dioxide. Carbon dioxide is a greenhouse gas linked to global warming. The greenhouse effect occurs as these gases act like greenhouse glass, allowing visible light to enter while trapping heat energy within the atmosphere. This visual demonstrates how the greenhouse effect functions to regulate the Earth's temperature by trapping outgoing heat. The combustion of octane is a prime example of a balanced chemical equation. It shows that for every 2 moles of octane burned, 16 moles of CO2 are produced. By knowing annual fuel consumption, we can estimate CO2 production. These calculations match observed increases in atmospheric CO2, confirming the link to fossil fuel use. Stoichiometry is the study of numerical relationships between chemical quantities. It allows us to predict product amounts, required reactant amounts, and reactant ratios. To understand stoichiometry, we can use an analogy like a pancake recipe, which defines the precise numerical relationships between ingredients. For example, if a recipe requires 2 eggs to make 5 pancakes, we can express this as a ratio of 2 eggs to 5 pancakes. Using this ratio, if you have 8 eggs and enough of the other ingredients, you can calculate that you will be able to make 20 pancakes. In chemistry, we apply this same logic to molecules. For the production of ammonia, the balanced equation acts as our recipe for combining hydrogen and nitrogen. The balanced equation for ammonia synthesis gives us ratios in both molecules and moles, which are more practical for chemical calculations. Using these mole ratios, we can determine how much product we can form from a specific quantity of a reactant, such as 3 moles of nitrogen. Stoichiometry also helps us understand real-world issues. For instance, when there isn't enough oxygen to burn octane completely, side reactions occur, creating pollutants like carbon monoxide. Moving on to oxygenated fuels, MTBE was once the common choice for fuel additives. However, it was found that MTBE does not biodegrade easily and has contaminated drinking water sources through leaks and spills. Because of these environmental concerns, ethanol, derived from grain fermentation, has become a widely used substitute to increase oxygen content in motor fuel, despite its higher initial cost. Beyond mole-to-mole conversions, chemists often need to calculate mass-to-mass relationships. We use molar masses to convert between mass and moles, while the balanced equation provides the ratio for the substances involved. To find the mass of carbon dioxide emitted from burning a specific amount of octane, we first convert the grams of octane to moles, then use the stoichiometric ratio to find moles of CO2, and finally convert that to mass. This solution map outlines the pathway from the mass of octane to the mass of carbon dioxide, utilizing the balanced equation and molar masses as our conversion factors. By applying the conversion factors systematically, we can calculate that 500 grams of octane will result in approximately 1.5 times 10 to the 3rd grams of carbon dioxide. Next, we explore the concepts of limiting reactants, theoretical yields, and percent yields, using another familiar analogy, making pancakes. If you have specific amounts of flour, eggs, and baking powder, the quantity of each ingredient determines the maximum number of pancakes you can produce. In this scenario, we find the limiting ingredient, the one that runs out first, which dictates our theoretical yield of pancakes. When things go wrong, like burning a pancake, we get our actual yield, which is usually less than the theoretical amount. The ratio of the actual yield to the theoretical yield multiplied by 100 gives us the percent yield of our process. In any reaction, the actual yield must be determined experimentally. It is almost always less than the theoretical yield due to side reactions or product loss during recovery. To summarize, the limiting reactant is completely consumed, the theoretical yield is the maximum possible product, and the percent yield compares the actual result to that theoretical maximum. For chemical reactions like synthesizing titanium tetrachloride, we can determine the limiting reactant and theoretical yield starting from given moles of reactants. Finally, remember that in industrial settings, engineers often select the most expensive or difficult to handle material as the limiting reactant to maximize process efficiency. Given 53.2 grams of sodium and 65.8 grams of chlorine, our goal is to identify the limiting reactant and calculate the theoretical yield of sodium chloride using a step-by-step solution map. To find the percent yield, we use an example where the actual yield is 86.4 grams of sodium chloride. Note that actual yield is often lower than theoretical due to product loss during the reaction. We can also perform these calculations for other processes, such as the reaction of copper I oxide with carbon to produce pure copper and carbon monoxide. This calculation relies on stoichiometric ratios and molar masses. We must relate the moles of each reactant to the moles of copper produced to determine the limiting factor. By following the solution map provided, we can determine the theoretical yield from the initial mass of reactants, which allows us to identify the limiting reactant for this copper production process. If we experimentally recover 87.4 grams of copper, we can compare this actual yield to our calculated theoretical yield to find the final percent yield of the reaction. Beyond mass and yield, chemical reactions also involve energy changes. Enthalpy is a measure of the heat evolved or absorbed by a reaction at constant pressure. Exothermic reactions emit thermal energy into the surroundings, while endothermic reactions absorb it. Enthalpy allows us to quantify these energy flows. The enthalpy of reaction, denoted as delta H reaction, defines the specific amount of heat exchanged when a chemical reaction occurs under constant pressure conditions. The sign of delta H indicates the direction of energy flow. A negative sign means energy is released, like a withdrawal, while a positive sign means energy is absorbed, like a deposit. This figure illustrates the difference between exothermic and endothermic processes, showing how energy moves either out into the surroundings or into the chemical system. Consider the combustion of methane. Because it is exothermic, its enthalpy of reaction is negative, signifying that heat is emitted into the surroundings as methane burns. Conversely, endothermic reactions, such as the formation of nitrogen monoxide, have a positive enthalpy value, indicating that heat is absorbed from the environment to drive the reaction. Finally, the heat of reaction is stoichiometric. The value of delta H corresponds specifically to the moles written in the balanced equation, allowing us to use energy as a conversion factor.